Hi guys, so today we're going to be talking about the antiderivative as a function of x. So the first thing I'm going to talk about is a definite integral as a number. So what we can see is the integral from a to b of f of x dx. So what we know by looking at this is that both a and b are going to be constants, which pretty much means that as we go and evaluate the integral, we're going to find a definite number for an answer. This is a little different from the next example I'm going to show. So the next thing I want to talk about is the definite integral as a function of x. So we have uppercase f of x equals the integral from a to x of f of t dt. So pretty much what's a little bit different is that we have an x here as an upper limit of integration. So our lower limit of integration is going to be a constant, just like we saw before, but what's different is that x, and it's going to be a variable. So pretty much what that means is that no longer are we going to find a definite answer like we did in the previous example, but we're now going to find a function of x instead of a definite number for an answer. Let's talk about this a little bit more so we can wrap our head around what we're really saying. So uppercase f of x equals the integral from a to x of f of t dt. So pretty much what this means is that it's an accumulation of the area underneath the curve of y equals f of t. So let's add a visual here. So here we have some function, we're going to label it f of t, just so we can see what's going on. So if we're going to integrate this, let's just say that a equals 0, and we're trying to determine what's the accumulation of this function to any value of x. So you would get the integral from 0 to x of f of t dt is equal to a function of x. So that's what we have here written to the right of the graph. So you can increase this to anywhere we really want. So this is what you're going to see in green. We can call it x1. And basically, we could put x1 into the function we just got, which is right into the right of the graph. And then we could find the accumulation of this function over this entire period. So now knowing what we just talked about, we're going to apply it. So let's use a little bit of a problem and let's work out an example. So find f as a function of x and evaluate it at the given x values. So here we have a graph of cosine, and you could tell by looking at it that the values that were given, which are 0, pi over 6, pi over 4, pi over 3, and pi over 2. So these x values, as you increase them, you're going to get a greater accumulation area. So 0 is going to be smaller, pi over 6 is going to be a little bit bigger, pi over 4 a little bit bigger, pi over 3 a little bit bigger, and then you're going to have the greatest accumulation area at pi over 2. So we're going to apply the fundamental theorem of calculus. So we're going to get this function into terms of x. So the antiderivative of cosine t is sine t, which we will integrate from 0 to x. So that means that sine of x minus sine of 0 is going to just equal sine of x. So again, this is the fundamental theorem of calculus. And we're going to take what's highlighted in yellow, and we're going to hold on to it, and we're going to plug our x values that we have here into the highlighted yellow portion. So let's move on to the next page. I'm going to continue to work out this problem. So this is the process of plugging in. This is the easiest part, so you just have to remember to do it. So we have our first x value is 0, so we're going to find f of 0 equals sine of 0, which is just going to give us 0. Then we got pi over 6, so f of pi over 6 is going to equal sine of pi over 6, which is 1/2. Same thing for pi over 4. F of pi over 4 equals sine of pi over 4, and that's just radical 2 over 2. And then we're going to continue to do the same thing for all the x values. So we got pi over 3 and pi over 2, and you're going to get radical 3 over 2 and 1. So we pretty much just confirmed what we talked about before we even started, which is pretty much that the x values are going to have an increase of accumulation, which is pretty much, it just means that your answers are going to get bigger once you move on from 0 to pi over 2, which pi over 2 is going to give you greatest, which it does, and it's 1. So let's try another example. So here we have f of x equals the integral from 2 to x of t squared plus 3t minus 1 dt at x equals 2, 5, and 8. So once again, we have our graph over to the right of t squared plus 3t minus 1. And similar to what we saw with the cosine graph, at the x values, you're going to get a greater area accumulation, which again makes sense. Let's see, though, if we can confirm what we're saying. So I'm going to pause. If you want to work this out, just pause the video right now and see if you guys get the same answer as me. So hopefully you guys paused it and you got the same answer. So just like we did before, we're going to get this function into terms of x. We're going to apply the fundamental theorem of calculus, and hopefully you got the same thing that I did, which is in the yellow box down below. So once again, we're going to carry this out to the next page, and we're going to plug in our x values. So we plug in 2, 5, and 8, and we get 0, 135 over 2, and 252. So just like we said before, we confirmed what we already thought, and the accumulation area is going to increase as we continue with x values. So hopefully this video helped you guys out and you learned a little bit about the antiderivative as a function of x.